So hello again. Tonight we're going to talk about the gravitational wave background. And if you don't know what that is and haven't heard of it, then I'll explain it. If you have heard of it, there's new data out. So you might have heard of the cosmic microwave background. That's that sort of ellipse-shaped thing that has the different colors on it, and they're representing strengths of microwave radiation, which correlates to temperatures during the early formation of the universe. And so it's everywhere, sort of the leftover heat pulse from the Big Bang. We've done a lot of studying on that. We've got a couple of probes that have measured it to the nth degree. And you'll notice that this particular map does not have that horizontal line through the middle of it. That's the Milky Way galaxy. You don't want to include that in the measurement. So when they did the last update, they subtracted that out. That's the local noise in the background image. They have to distinguish between what's local microwave stuff and what's cosmic background microwave stuff. Well, turns out from the analysis of gravity waves that there is also a gravity wave background. When they first said that, nobody believed it because the only gravity waves we were looking at were from things like collisions of black holes and neutron stars, and those were like one over here, one over there, and they were infrequent, and there weren't enough of them considered to make a background. So nobody believed it until, instead of using the LIGO and Virgo equipment to detect gravity waves, they used a new approach. And when they used a new approach, they found a lot more background gravity waves. So they just, let's give this thing a name, the gravitational wave background. Yeah, that acronym doesn't parallel the cosmic microwave background. It should be the GMB, or the GWB, as opposed, So anyway, gravity waves are not a form of detected electromagnetic radiation. So a gravity wave itself is not radio, infrared, visible, UV, X-ray, or gamma ray. It's actually the fabric of the universe expanding and contracting, the distance between molecules and atoms increasing and decreasing at the nanometer level, the fractions of the width of a proton kind of thing. They're not direct measurements, so they're indirect measurements of something changing, and so that's how they detect it. So here's how we used to detect gravity waves. This is kind of a close-up. The actual tubes, the tunnels that extend down in that sort of inverted V shape, actually go out about 4 kilometers. They're concrete tunnels, and inside the concrete tunnel, there is a metal tube, and the metal tube has a vacuum applied to it. And at the ends of the tube are highly polished mirrors, and they're very, very heavy mirrors, and they're suspended on quartz fibers. And at the center, they have a powerful laser that they run through a beam splitter, and one part of the beam goes off that way, the other part of the beam goes off 90 degrees to that way. The beam goes out, bounces off the mirrors, comes back, and then is remerged with a beam joiner to create an interference pattern. So if the length of this tube is just atomic level longer or shorter than the length of this tube, then you'll see it as, instead of the interference pattern negating itself, there'll actually be some residue left over, which will cause light and dark areas on the detector. So that's how we used to measure gravity waves. But what that means is the frequency of the oscillation of the fabric of space has to be pretty high. And the amplitude, like how hard it expands and contracts, relatively speaking, has to be fairly high in order for it to be detected using this technique. If all you can see is green light, then you don't know that other colors of light exist. Same sort of thing with gravity waves. If the only thing you can detect is a specific wavelength range of gravity waves and a certain minimum amplitude, then that's all you'll ever see. But if you come up with a new technique, then maybe you'll see gravity waves you didn't see before that have always been there. And that's what they did. There's a thing called a pulsar timing array. You can think of a pulsar kind of like a lighthouse. It just spits out a beam of energy every so often. The amount of energy and the exact period is down to the very, very small measurable oscillations. So you can easily filter out anything that is a disruption to that pattern. If a beam of energy coming off of a pulsar normally takes a certain amount of time to get to the Earth, and we can measure that down at the not nanoseconds, but femtoseconds, a thousandth of a nanosecond. If that changes, we can detect it. Now, if that changes over a very short period of time, that's a higher frequency fabric shift. But let's say it varies by a very small amount over maybe a year. That's a very long wave, very low amplitude wave. And this is what they originally found when they created their pulsar timing array. Is they found gravity waves that are very, very long wavelength, like light year plus length wavelengths at very, very low amplitudes. They have to amplify the signal a lot to see that it's even there. So as they started looking, they found these things, but now they had to get corroborating data. And so they looked at it for better part of a decade to actually, get the noise level down low and the signal level up high. And so they said, we think we found lots of gravity waves. Now these are in radio because they're pulsars, but you need to detect this weak a signal, you need lots of giant radio antennas as an interferometer spread across the Earth, and then you collectively merge those signals, and you need to watch not one pulsar, but maybe hundreds to many hundreds of pulsars. So you can see that not only is it the fabric of space expanding and contracting in maybe two directions, it might be in multiple directions. So you want as many feeds on this as possible. And you have to be listening in 24/7, because when you're pointing the other way, you need to be listening to radio in that direction. So you want it to be a global effort. So they went back and said, let's get some other countries involved. Let's get some other radio arrays involved. Let's do this big time. So initially they had a report that involved, this was back in 2013 is when the US first started this with nanograv. And then they added in Europe, China, and India, and then South Africa. So they collectively put together their first report in 2023. And they said, well, here's what we found out. There is expansion and contraction of space. We looked at it over multiple years. Gravity waves with frequencies in the light year plus wavelength at very low amplitudes. Yeah, we see them. And you're not going to be able to corroborate this with LIGO and Virgo because they just can't detect these kinds of things. So in May of this year, they put out a second report. They got more data from more sources, merged it with the rest of the data, and they not only said it's confirmed there is a cosmic gravitational wave background, but we have been unable to pinpoint all the sources because there's so many of them. It's very noisy. And we have to filter out all of the locally occurring things like black hole mergers in our galaxy, neutron star switch on or transition to black hole in our galaxy. So you have to filter out all the more recent stuff, all the nearby stuff, before you can see the background. Kind of like us having to filter out the plane of the galaxy in the cosmic microwave. But yep, they're referring to it now as the stochastic background gravity wave. So as I said, they have to filter out the early universe versus today, and they haven't completely done that. So at some point, they're going to come out with a map of the cosmic gravity wave background, but not yet. They're still researching it. So they have made a postulation as to what might be the source for this initial cosmic background gravity wave, and they've called it ultralight dark matter. Whenever you can't explain something, just attribute it to dark matter. Now we have another flavor of dark matter called the ultralight dark matter. Should Michelob be making that? Make Michelob ultralight dark matter? Anyway, the ULDM, as they're calling it, you would have to have a couple of things prerequisite in order for it to actually be this thing. You'd have to have blue tilted inflationary spectrum, which basically means when the initial universe switched on, everything went boom, then the wavelength of the light that would be emitted would have to not expand in all wavelengths. It would have to expand like shifted towards blue. Now, blue is higher energy. It's also things coming at you from a Doppler shift perspective, but we see things that are red shifted, not blue shifted. And the primordial spectrum of scalar perturbations would need large numbers. This is basically saying there would have to be a lot of different sources of gravity waves to make up all that we're seeing. It's not just a few. ULDM is kind of like the verdict's out, but it's their current postulation. So here's a thought. Earthlings at one time used a tree branch, eventually a blanket, and modulated by waving it as low power, low frequency smoke signals for communication. And it was used in a lot of places. Mountaintop to mountaintop. This is how we communicate. Long time ago. But then later on, we found out, radio works much better at this. So we increased the amplitude, pumped up the energy, kilowatts, megawatts, and then we increased the frequency from, shortwave to microwave to, very high gigahertz signals that we use nowadays. Much better. So when we find something that doesn't work, we find a way to do it better, and then we just keep tweaking that to get it better and better, more advanced. We've, since the invention of radio, done a lot of interesting things, like we've replaced analog with digital signal processors. We've used things like the multiple channel modulation techniques, where we'll actually transmit across multiple channels, and then we'll pick whichever one has a good reception and then merge those signals together to make a higher speed connection. Bluetooth uses that today. The original Wi-Fi used it, but doesn't use it anymore. If we're looking at gravity waves as this background noise from multiple sources at multiple wavelengths, maybe somebody's trying to say something, and we're just standing there with our blanket going, I'm signaling, is anybody hearing me? I can't hear anybody else. It's kind of like the background gravity wave is not detectable by LIGO and Virgo. They're just different kinds of instruments. So you're deaf to it. Well, if we never come to the conclusion that, hey, maybe we should try demodulating some of these very long gravity wave signals that can travel at light wave speeds across the universe. Maybe we'll find out that the universe is actually noisy, full of communications that we just have yet to learn how to demodulate and understand. And someday we'll be better than the guy with the blanket on the mountaintop trying to signal people. We'll find a way to modulate gravity waves, not just demodulate them. But nature already knows how to emit gravity waves. You just need to have, like, two black holes collide. Big gravity waves. But do you need that? If you think back to the early days of radio, they had these, megawatt class AM transmitters on the east coast of the US and the west coast of Europe, and that's how they would transmit across the Atlantic Ocean. Of course, nowadays we just use microwave up to a satellite and down from the satellite, and it's maybe 20 watts. We've got direct TV satellite dishes that are picking up microwatts of energy and pulling a signal out of it using digital signal processing. So maybe we need to start paying attention to the cosmic background gravity waves the same way. Well, it turns out that the Earth can generate gravity waves all by itself. These are very short duration, less than a year in wavelength, but certainly more than a few seconds in wavelength. Turns out ocean waves, seasonal tides, as sort of the moon pulls on many, many, many tons of water and it slushes from low tide to high tide, that moving mass generates a detectable gravity wave. The second thing is minor earthquakes. When you have large pieces of rock going rumble, even it's like, 4 on the Richter scale, which is, hey, did something bump into the building? These generate gravity waves. They're just at a different wavelength than LIGO and Virgo can detect, and they're at a much smaller amplitude. So maybe all we need to do is figure out how to take a mass and accelerate and decelerate that mass to move it back and forth to act as a modulator for gravity waves. And we can signal out to say, I'm talking to you. Is there anybody out there? Maybe we'll send one of those funky digital binary pictures, because the guys out there probably don't speak American English. But then again, my guess is they've been watching us and listening to us much longer than we would have the ability to communicate with them in gravity waves. So we may not be able to speak their language, but if they've been around for millions to maybe a couple of billion years longer than us, they more likely have a way of having a Google Translate. So in conclusion, yes, after a second corroborated report, there appears to be a cosmic microwave background and a gravitational wave background. They're not oscillations of the electromagnetic spectrum. They're oscillations of mass amounts of gravity. These are extremely long, maybe on the order of light years length, and the frequencies would, if you inverse that, the frequencies would be at the billionths of a wave nanohertz level. So if you're thinking about terahertz and microwaves at megahertz and amplitudes at kilohertz, and this is less than 1 hertz. This is fractions of 1 hertz. So a billionth of 1 cycle per second. So it takes a billion seconds for 1 cycle. The current presumption is that this gravity wave background is left over from the early formation and expansion of the universe, but we don't know what the source is precisely. We've evaluated these using pulsars. We need to filter out these from the background so we can come up with that background picture of gravity waves. The actual source of them is still under discussion, just as we abandoned modulation techniques and have gone with radio or the electromagnetic spectrum. Now, maybe in 100,000 years, we'll go, that whole electromagnetic spectrum stuff, that was interim. That was like smoke signals. Now we're modulating gravity waves using this tabletop gravity wave modulator that we just built. If you can do that, maybe you can speak. And the first thing to do is learn how to listen, obviously. Always learn how to listen before you get arrogant and try and speak. So lots of links this time out. And then there's actually an article, Modulation of Gravity Waves. That's about ocean wave movement and earthquake wave movement. Okay. Comments? Questions? I know, something to think about. Ponder.
Yeah. Yeah.
These waves lose energy as they spread out over billions of years.
Well, that's the thing. If you're talking about photons, particles of energy or wavelengths of energy, yes, they do go through a spreading out and a reduction. But that doesn't mean we can't detect them. The same thing might hold true for gravity waves, but we're seeing that they we can detect gravity waves in different directions. So even though we're not dead on target with the source, we can still get a piece of that, amplify it, and detect it, just as if it was, photons from a distant star. I just think that we shouldn't get too hung up on the way things are. We should be open to, that sounds different, but I can see the analogy between one thing and another. I can see where that's going to lead. Have the faith in the progression of technology that once we find something that's meaningful, we can then turn to all of our analysis skills, all of our spectroscopic skills, and maybe there's more to this that once we figure it out. I was watching an interview of somebody who grew up way out in the outbacks of Canada, and when she was growing up on the farm, there was no communication with the outside world. There were no TV channels. Back when she was growing up, they didn't have satellite TV, and she grew up not having watched all this plethora of junk that we grew up watching on TV, listening to on radio. And her first dose of that stuff was watching, when she finally got internet access because she moved to New York City. Yeah, it was a culture shock, all this stuff, that it existed back then, but she had no ability to receive it, so it didn't exist until she got to the point where she had access to the technology to receive it. Same sort of thing. The cosmic gravitational wave background has existed for billions of years. It's happening right now. It's kind of like neutrinos. Billions of them are going through your body right now. You just have no way of feeling it, detecting it, measuring it, and therefore it doesn't exist, right? Well, gravity waves can do the same thing. If you can't detect them and they're there, you never know they're there. But once you know they're there, it's kind of like saying, I never knew there were so many mosquitoes until I went out to the Everglades of South Florida during the rainy season. And now every time I go to the Everglades, I think there's just millions of mosquitoes around me. Well, yeah, that's kind of normal. You don't know what's there until you know what's there.
So gravity waves travel at the speed of light, is that correct?
From what we can tell, light travels the fastest, and then gravity waves travel a little bit slower. We're not sure why. And then the thing that travels just a touch slower than that is radio signals, electromagnetic spectrum, normal stuff. So it may be that when one of these gamma ray bursts occurs, there's actually a gravity wave detection that could occur first, but we don't have the instruments to detect it.
Yeah.
But now I'm tied into the NASA GCN. Every day I'm getting 5 to 10 gravity detections from LIGO and Virgo, and then I get the corroboration from the other observatories. The gamma, the X-ray, all the other detections to. Hey, a day later, we finally got the ultraviolet from that gamma ray burst from the same source. So slightly different speeds, but then you ask yourself, why is it that gravity waves propagate through the fabric of the universe at a different velocity than do photons? How about neutrinos? When you have a stellar explosion like a supernova, the precursor you look for are neutrinos. You don't look for the light because the light will come by maybe a day later. You look for the neutrinos first because they're less susceptible to any slowing down by the fabric of the universe. Why? Because they're weakly interacting. So
James Webb can see galaxies back to 13 billion something years old. So that's fairly close, the word close in air quotes, to the age of the universe.
Well,
So
here's the thing. Here's the thing
gravity
that
waves, the gravity waves from, if these gravity waves are from the formation of the universe, then at some point they should finish washing past us to where we wouldn't detect them anymore. Or that's what it seems like to me. I mean, if it's
well, the same thing
because,
could
I
be
mean,
the
I'm
same
sorry, go
thing.
ahead.
The same thing could be said for light. If, for example, the turning on of the universe
Yeah,
produced a pulse of energy, a light pulse,
yeah,
how long did it last? Oh, maybe I don't know, a billion years. So at the first sign of detection, we should be able to see that for a billion years. And after a billion years, the cosmic light will go off because it's done. I agree. The same thing should be true for gravity waves. If the gravity wave background is from the initial pulse of the formation of the universe, then
yeah,
how long did that last? Was it very brief? Was it long? We're now detecting it. Seems rather convenient that we're detecting it at this point in our technological lifespan. How long will we be able to detect it? Well, that's an unknown because we don't know what the source of it is. So we don't know what the duration of it is. If the duration of it happens to be, a million years, and we just now started detecting it, we probably will have another, 900,000 years of gravity wave background before it just goes dark. But then on the other hand, we have the expansion of the universe and it's accelerating. So things at the outer edge are moving away from us because the universe is expanding. And when the outer edge of the universe has accelerated to the point where it's near the speed of light, the light will take longer and longer and longer to get to us. And at
yeah,
some point, the outer edge of the universe will start to get dimmer and darker because those stars, those galaxies at the outer edge will now be moving away close enough to the speed of the light, to the speed of light, that they're exceeding the expansion rate of the universe because the universe is not currently expanding at the speed of light. So once you start blowing up the balloon beyond the speed that it can transmit the data to you, you can no longer see the outer edge and things will start to disappear. Early on, they attributed that it's instrument error, but you've got a better instrument. It should show more things, not less things. And then they've attributed it to, well, maybe it was along a seam where you glued a seam together in an image and you just had it overlapped a little bit, and therefore those stars disappeared in the overlap. The images are now gigapixel. So the photographic plate seam overlap seems less likely. They don't know why. They just know that, and these are not galaxies that are disappearing. These are stars in our galaxy that are disappearing. And the only thing they can come up with is maybe the concept of a star collapsing into a black hole has an unusual variation where it doesn't go supernova to collapse into a black hole. It just does a direct gravity collapse into a black hole. And the only thing we're going to be able to measure that with is gravity waves. We won't be able to measure it using the electromagnetic spectrum because the energy source was there and then all of a sudden it's not there. And there's no like debris cloud to say it went nova. It's just not there anymore. So some of the things that we think we know, some of the things that we postulate as we advance the technology and we observe more, some things might need to be touched up.
Before we mentioned the age of the universe, well, I understand what I read. It's calculated 45 billions. Is that the latest stand of things?
Well, we used to think how long it took for a galaxy to form or a galaxy of a certain size to form. And we had a number of better part of a billion, certainly many, many millions of years before you can have a galaxy that's that well organized. And with the James Webb Space Telescope, we're finding galaxies at the limit of its observational capability that are already fully formed. And then when we measure the redshift, it's like, it's more than 13 billion years to that galaxy, 13 billion light years to that galaxy. How did a galaxy that large get so well formed from where we think the beginning of the universe is until what we see?
Mm.
So, I never stand too solidly on what you think of as factual if what you're standing on was shaky ground to begin with. So if you think that the universe in infrared light is 13.8 billion years, you're not including all that you know. We also observe the universe to a very fine degree of accuracy using global radio telescope arrays. And that can see out maybe another 100 billion years farther. So instead of it being 13.8, it's closer to 13.9, which doesn't sound like a lot, but if you're judging the age of the universe being off by a couple of 100 million years, that's significant, because that's the time you're saying it took to go from the initial switch on of the universe until stars formed or galaxies formed. Now, if that's now, another 100 million years further out, standing on shaky ground. But also, if we think the universe is 13.8 billion years from us to the outer edge, that's how long the light took to get from where it was to us.
Right.
What did that light source do if the universe is expanding and accelerating while that light was traversing the universe to get to us? So it shouldn't be 13.8. It should be 29.6, right?
There you are. That's already something.
So that's just kind of a common sense thing to think about, is if it's expanding and accelerating, the stuff that's out the outer edge, and it's taken 13.8 billion years for that energy to make it to us, for us to detect it. What was that thing doing in that 13.8 billion years? It was moving out even further. So what is the diameter of the universe? It's got to be twice that. But that's only what we can detect, that we have detected so far. The universe could actually go out even farther than that, and that light just hasn't gotten to us yet.
Yeah, you are. Exactly.
So how big is the universe? I think the most appropriate answer is we have some guesses, but we don't know for sure, because we haven't seen everything out at the edge yet.
Yeah. Well, the hope is with the new telescope, the Webb,
Well,
to see some more.
we do know that as they refer to it, the crisis in cosmology between deep space radio astronomy and deep space infrared astronomy has kind of said, well, yeah, we know there's a difference between the two, but if we just say that's kind of instrument variations, and instead of having a line for that math, we have a fuzzy tube, then both of them line up within that fuzzy tube. So there's not really a crisis in cosmology, because whenever you take a measurement and it's a scientific, fact-based measurement, it won't be a number. It'll be a number with some digits at the end that have parentheses around them. It's like, well, different instruments gave us different variations all the way out this many digits. Or it can be, well, we know the tolerance of the chemistry of the instrument used to make the measurement. So it'll be this number plus or minus some factor. So a good measurement is one that has some variance in it. And if it has too much variance, it's not a good measurement. If it has lots of digits, if it's got at least like 5 or 6 digits before you get to the parentheses, or the plus or minus are like 5 or 6 digits out beyond the decimal point, that's probably a good measurement. And then if you can get multiple observatories using multiple kinds of instruments to make the same measurements, probably a good measurement, but it's only what you know there. It's only the observation you took. You can take another observation a year from now and things can change. But that's, if we make measurements of stuff in our solar system, there are changes that take place every few days. For example, the moon Io has a very volcanic surface, lots of flows going over it. So if we take a picture of the terrain of Io, come back a month later, take another picture, the terrain is dramatically different. There may be some very tall volcanoes that act as kind of like anchors because they're at the high level spewing outward, but all the lower level volcanoes have already been covered over by the debris flow, by the pyroclastic flows, and by the lava, so the surface changes. So don't expect anything to ever be static in the universe. It's moving, it's changing, it's growing, it's shrinking. To quote John Lithgow when he was observing Jupiter in the movie 2010, it's shrinking, it's shrinking. Okay. Any other comments or questions before I stop recording?
Yeah, with the cosmic gravity wave background, were they able to detect a direction that it was coming from?
Like the cosmic microwave background, it's pretty much everywhere. It's coming from all over the place. So they have no single source. They have lots of different sources at different amplitudes and different wavelengths. So that's why it's called a stochastic background, or just a background and it's everywhere. It's kind of like the microwave background, and it's everywhere. Now, once we have better detectors, I'm sure we can finesse out, this signal is stronger than this signal, or the signal in that direction is this frequency versus that frequency, but we haven't tweaked things down to that level yet.
Very interesting.
That's why I do them. Comments or questions before I stop recording?